welcome to lesson 5.8. We are going to look at quadratic formulas. So this is the last part of the chapter. This is a catch-all way, any quadratic equations. So all the ways that we've done so far, solving by square roots, factoring, graphing, completing a square, things that we solved before could be done by this method as well, plus everything else that you can't do with factoring or square roots or graphing, which is all the imaginary solutions. So everything can be solved by quadratic formula. Some people choose just to do quadratic formula the whole time, so that way it takes all the guesswork out of which method should I use. That is a strategy, and that does work, especially when your tests are not timed and you're at home anyway. So consider that as we move through this lesson. Two parts to the objective, because there's essentially two parts to the formula. There's a part of the formula called the discriminant, and it allows you to determine the number and type of solutions you're going to have before you even get the solutions. And then there's the rest of the formula. So we're going to look at it in that way. We're going to look at the discriminant first and then the rest of it. So let's talk about the discriminant. The discriminant is the value of the expression b squared minus 4ac when you have the equation in standard form. So the a, b, and c that we've talked about before are the a, b, and c that are in that formula. When b squared minus 4ac is positive, there are two real solutions. So examples of what that could look like are this and this. We've talked about how you can get two solutions, one solution, or zero solutions, zero real solutions. The discriminant is what can show you that algebraically before you even graph it. And remember, solutions are where the parabola crosses the x-axis. If b squared minus 4ac is exactly equal to 0, there's one real solution. And what that looks like could be something like this, where it's touching it once, or something exactly like this. Doesn't matter if it's opening up or down. If it's touching the x-axis once, there's one real solution. If b squared minus 4ac is negative, there are zero real solutions, but there are two imaginary solutions. And that could be something that opens up that's fully above, or something that's below and opens fully down. It's not touching the x-axis. So the objective stated that you can use the discriminant to tell you the type and number of solutions. So we're going to do that with these three examples. We're not going to actually find the solutions. We're just going to figure out how many solutions we have and what type they are. So remember, this is the A, this is the B, this is the C. We're finding b squared minus 4ac. So you're substituting those numbers in, okay? So b is -5. Remember, if it doesn't matter, that's negative because you're squaring it, so that part will become positive anyway. And then you have minus 4 times a, which is 3, times c, which is -2. -5 squared is 25. -4 times 3 is -12. -12 times -2 is positive 24. So you end up with a discriminant that's 49. It doesn't matter that it's 49, other than the fact that it's positive. Because that number is positive, there's two real solutions. X squared plus 5x plus 10. Substitute the numbers in just the same. So remember, a is 1, b is 5, c is 10. So b squared is 5 squared minus 4 times 1 times 10. You end up with 25 minus 40, which is -15. -15 is a negative number, so there's 0 real and 2 imaginary solutions. I'm going to pause it, you try C on your own, and then we'll compare answers. So in this one, b squared minus 4ac, b is 6, a is 1, c is 9. You end up with 36 minus 36, which is 0, so your discriminant is 0, which results in one real solution. So that's how you use the discriminant. Now let's look at how to use the entire formula. So the entire formula, notice that the b squared minus 4ac is in there. You take the square root of the whole thing, and then it's also the opposite of b plus or minus that number all divided by 2a. And that is the formula. See if you remember what the opposite of b over 2a represents. That was all the way back to the first lesson where the x-coordinate of the vertex is the opposite of b over 2a. That's that part. So those are the two parts of the formula. So here's the first one we're going to solve together. The first thing you need to do is get the equation in standard form. So you have 3x squared minus x minus 4 after both sides. And your a is 3, your b is -1, your c is -4. I still like to find discriminant first. I'm not going to substitute everything into the entire formula because I'm going to work with just this part first anyway. And then we can build the rest of the formula around it. The opposite of b, well, I'm sorry, b is -1. So you end up with -1 squared minus 4 times a, which is 3, times c, which is -4. So you end up with 1. -4 times 3 is -12. -12 times -4 is -48. So you end up with plus. So you end up with a discriminant of 49. That 49 is the expression underneath the square root. So I'm just going to go ahead and take the square root of it, and you get 7. The rest of the formula is the opposite of b. So in this case, that would be +1 since b is -1, plus or minus that number 7 all over 2a. A in this case is 3, so 2 times a would be 6. Understand that represents two different numbers. One is 1 plus 7 over 6. The other is 1 minus 7 over 6. 1 plus 7 over 6 is 8 over 6, which reduces to 4/3. The other one is -6 over 6, and you end up with -1. So those are your two solutions, x is equal to 4/3 or -1. Let's try another one. So 3x squared plus 24x plus 40. The numbers are a little bigger, but it's really no different. Again, b squared minus 4ac. You end up with 24 squared minus 4 times 3 is 40. 24 squared, I don't have memorized off the top of my head, so I'm going to quick punch that in. You get 576. And then it's minus 4 times 3 times 40. So minus 480. So you end up with 94, 96. Okay. So that's the number under the square root. What we're going to do is simplify that radical. So unlike example A, where we got 49, which is a perfect square number, we got a number that's not a perfect square. But I think it has a square factor. If I divide 96 by 16, what do I get? You get 6. So you can split 96 into 16 and 6. You want to get it fully simplified at this point, like a simplified radical. So 16 will come out as 4, and that 6 will stay. The opposite of b In this case, b is 24, so you have negative 24 plus or minus 4 root 6 all over 2a. A is 3, so you end up with 6. If you can divide something out of the constant, the coefficient, and the denominator, you need to. So I can divide a 2 out of 24, 4, and 6. You're not dividing out of the radical. That simplification happened in that step there. So when I divide a 2 out of everything, you end up with negative 12 plus or minus 2 root 6 over 3. You can leave your answer like that. You may also see the answer split apart. What I mean by split apart is one's plus, one's minus. So you could say that the answer is negative 12 plus 2 root 6 over 3 and negative 12 minus 2 root 6 over 3. Writing your answer either way means the same thing. Whether you split it up or leave it as the plus minus, there's two solutions. So that's a situation where the solutions are irrational, and you could not do this by factoring. That's the one we already did. So what's good about the quadratic formula is even if the solutions are imaginary, you can get a solution with the quadratic formula as well. So again, this what we're about to do is one you could not get by graphing or factoring or any other method other than completing the square, but this is better than completing the square. Faster, I would think, especially when the numbers are what they are here. First thing I would do is get it in standard form. When it's set up like this, I would actually just move the quadratic term to the other side. It's better to have that positive. So now we're just going to do the same process we just did. It's just I'm letting you know ahead of time it's going to be imaginary at the end. B squared minus 4c, that's the first thing. B is 4, so you get 4 squared. Minus 4 times a, which is 2, times c, which is 3. 4 squared is 16. Negative 4 times 2 is negative 8. Negative 8 times 3 is negative 24. So you end up with negative 8. So your discriminant is negative 8. That's why you know that this is going to be imaginary at this point. Simplify the radical. We're going to take a square root. Negative 8, you can split into negative 4 and 2, where the square root of negative 4 is 2i, and then that 2 will stay. We're going to build the rest of the formula around it. The opposite of b is negative 4, plus or minus everything divided by 2a, which is 4. So between negative 4, 2i, and 4, even though that's imaginary 2i, you can divide a 2 away from it, so we will. So we're going to divide a 2 from that, and you're going to get negative 2. You're going to divide a 2 from that, you're going to get 2. You're going to divide a 2 from 2i, you get I. Your answer is going to be negative 2 plus or minus I root 2 over 2. And there's nothing else you can do there. I'm going to leave this one for you to try. So get it in standard form. And then just apply the formula. I would find the discriminant first, just like I did, and see what you get. So give that a try. So as you can see here, we added 4 to start. Got to get in standard form. We found the discriminant. The discriminant in this case was negative 44, again indicating that it was imaginary solutions. I simplified the radical by taking out the negative 4 and getting 2i root 11. Then I built the rest of the formula around that. The opposite of b was negative 2. 2a was 6. Divided a 2 out of everything, and you ended up with negative 1 plus or minus I root 11 over 3. Got a couple more to try here. We're going to save these for an exit ticket. So you can give them a try, and then we'll go over them as in an exit ticket at the end. In context, if you get a question like this is a really typical SAT type question, where you're given a model, like a quadratic model to represent something. In this case, it's profit that a company is going to make by setting a variable price. So if you think about it, right, like there's a perfect price somewhere for selling things. If you set a price too low, you might sell a lot, but you're not making enough per transaction, so you're not going to make as much profit as possible. You set the price too high, no one's going to want to buy the thing. There's some price in the middle that is like your ideal price. So that's why a quadratic model kind of makes sense for this as opposed to like a linear model. The question here is, will a profit ever exceed $5,000? You can answer this question by finding the discriminant. So it's just a yes or no answer. What you're going to do is substitute that 5,000 in for P. What we're going to do is evaluate the discriminant to determine if this is possible or not. If we get a positive discriminant, that means this is possible. If we get a negative discriminant, it means it's not possible. It's really that simple. So we're going to set this in standard form. So we're going to subtract 5,000 from both sides. You end up with 0 is equal to negative r squared plus 500r minus 64,500. The discriminant is b squared minus 4ac. So in this case, b squared, well, b is 500. It's minus 4 times negative 1 times negative 64,500. So when I turn this in the calculator, let's see what we get. So you get 250,000 for 500 squared. And you get 258,000 for that part. So you end up with negative 8,000 as the discriminant. Since that's negative, the answer to this question is simply no. The only solutions to this equation would be imaginary, so it's not possible in reality. We have one question left that is very similar. It's just a different setup, or a different scenario, but it's the same idea. Throw a ball up, a wall is 17 feet high. You have a model that represents the height of the ball, given the amount of time that has passed since the ball left the person's hand. Can the ball go over that 17-foot high wall? So you're going to take that 17, substitute it in for h, and then find the discriminant. If the discriminant is positive, the answer is yes. If it's negative, it's no. So I'm going to leave that one as an exit ticket question. We'll go over it together, but give it a try first. All right. Let me know if you have any questions.